going to go over OpenAPI using a OpenAPI Dissector from GitHub, and then using my 5GC pcap that I just use when I run a TCP dump from the 5G core side, and then I obviously just dump it into Wireshark. But so here is the GitHub page for the OpenAPI Dissector. So it goes through it pretty well. I'm running this on my MacBook, which I do all my analysis on. I had some issues with installing this on my Ubuntu 22.04 machines. Still working through that, but for the most part this should work. So I just did a git clone of this directory here, and then you go in, let's see, so if I go home I can see it's right here. So I'll go see OpenAPI Dissector, and then I go into generator. That's there. So, and then it's asking you need to generate a spec file. So this OpenAPI_spec.lua, derived from a specific 3GPP release. This can be done a few commands, blah, blah, blah. So if you go to this website, or I mean, you can basically just use what they're telling you in the instructions here. But if you go to this website, you can browse between different 3GPP releases. So you're going to want to at least what the version that the software, so 3G, Open5GS and SRS-RAN are running. So release 17 works as far as what I've seen. So again, you can go in there to that generator, run this git clone command, and then run the Python 3 generate.py. Again, that's right there. That's going to process the specific YAML files, and then they're going to be copied into this 5GC API subdirectory. So again, if I go into that 5GC APIs, there's everything that it pulled from there after I ran the generate py. And it also generates this OpenAPI spec.lua. So you also need to go here, download the json.lua contained from that repository. So this guy right here. I think I just ran, a wget on the raw file here and pulled that in. And you can pull that to wherever, because you're just going to copy it to a Wireshark directory. So now you're going to have to take that OpenAPI spec.lua, the json.lua that you just downloaded, and then there's two other Lua files that are in the source directory under OpenAPI Dissector. So here's the JSON validator and the OpenAPI Lua. You're going to have to take those, and so if you go to Wireshark, and it's going to be different if you're running on Ubuntu or Windows, then you're going to have to go to Help and then About Wireshark. But for me, I just go to the Wireshark on my Mac, go to About Wireshark. You're going to go to the Folders tab, and then you're going to look for Personal Lua plugins. And that is where you're going to put those 4 files in. So I've already got them loaded, so I can go in and see a couple of those. Show the JSON.lua, OpenAPI, Lua, OpenAPI _ spec Lua, and the JSON validator, all right there. So they're already loaded in. You're gonna have to reboot or restart Wireshark. There is a way you can load the plugins, reload your Lua plugins under Analyze, so you could do that as well. So now we can go to our pcap file, and so there's going to be quite a bit of information depending on obviously how long you ran the TCP dump for. This has 1,485 packets in it, as it is. But so I like to run the OpenAPI and SCTP filter. That way I can see all the OpenAPI messages that are going on, but then I can also reference certain procedures that are happening within the 5G core. So just to establish some context at what we're looking at when we're seeing the source and destination with the default Open5GS network configuration. So we've got this list here from the Open5GS documentation of all of the local addresses assigned to each network function. So MongoDB, that's going to be the web UI, the subscriber database. That's when you log in on the actual machine and you go to a browser and you type in localhost :9999. You're going to be able to access that as long as the 5G core is running. All these other network functions are assigned the appropriate IP address or loopback address. But what we're going to see here on the OpenAPI side is we're going to see, this .1, which we see is assigned to the MongoDB, the subscriber database. That's also going to be associated with the AMF. So if we look through all of this information, we're not actually going to see any of the .5s. We might see it on some of the SCTP. Actually, no, so we're not on this instance because you can see here, so this .173 is my core network, and this .225 is going to be the G-Node B. So a little different than how I set it up in the last video. This is when I was running, the SRS ran on one machine and Open5GS on another machine, and then connecting them through a VPN. So we won't see that, but again, when we're looking at OpenAPI, the .1 is going to be the AMF as well. So again, we can see, the AMF talking to the network repository function. It's also communicating with this .200, which is the communication proxy. So a lot of the initial setup is going to be between those entities, AMF, the NRF, and the SCP. Once we get into a lot of the actual device procedures, so again, the registration request, it still has to communicate with the SCP and repository function, but then it's also going to be communicating directly with, here is the .11 for the AUSF, .12 for the UDM, and the .20 for the UDR. So we'll see a lot of that. But again, we can just reference this right here for when we're looking and seeing some of those procedures happen. This is the NG setup request and response, so that's just the G-Node B connecting to the core network up here, obviously this is going to be, when I turn the 5G core on, this is going to be all the network functions kind of, discovering each other and working with the SCP. So the communication proxy and the network repository function. So that's just, the initial setup procedure for the 5G core. This is the G-Node B connecting, and then we go further down. There's more setup procedures going on. But then we can see when the device, handset, SRS UE, whatever, is starting to interact with the 5G core. So now I can reference what's going on procedural wise with the OpenAPI messages. So here I see that the initial registration request is coming into the core network, and then we can start seeing all of the subsequent behavior for the AMF is going to query the AUSF for authentication. The AUSF is going to get the SUCHI value from the AMF, and then it's going to forward and query other network functions. So we've got the UDM and the UDR. So the AUSF is going to send its information that it received from the AMF to the UDM. There's its SUCHI value, and then it's asking for security information for it to generate authentication data. So the UDM has to then query the UDR, which is connected to the subscriber database or the web UI, to get authentication data and authentication subscription information. So the UDR is going to get the the permanent key, the OPC key, the AMF, and the sequence number, and then it's going to send that back to the UDM. The UDM is going to generate the authentication vectors. The authentication vectors are going to then be forwarded on to the AUSF, and then to the AMF. So then the AMF will send the authentication request to the UE, which includes the authentication vectors, the RAND and the AUTN, and some other parameters as well. The UE is going to calculate based on those vectors, and it's going to send a response in the authentication response. Again, the AMF is going to receive that, send it to the AUSF to confirm that the response matches the expected response that is stored in the AUSF. So it's either going to be successful or not successful. Upon a successful authentication at the AUSF, it's going to forward that success onto the UDM and UDR, so they can store that authentication status, and then it's going to also send that back to the AMF. The AMF is going to based on what the security algorithms that the handset or UE is capable of, that it sends in the registration request. The AMF has chosen, what encryption and integrity protection algorithms it's going to use for NAS messaging, and it's going to send the security mode command to the UE. The UE is going to receive that. It's going to, again, do some calculations. It's going to verify the integrity of that message, and then it's going to respond. And usually too, within this security mode command, the core network is going to query for the IMEI SV. So if I go into the message here, I will probably see that Yep, we've got the mobile identity, the IMESV is being sent to the core network now. And then within that, the in commercial networks, the core network is going to take the IMEISV, send it to the 5G equipment identity registration to verify that that handset or that device is not blacklisted. There's a lot of other processes that kind of go on after this point. So the AMF is going to, request some subscription data, from the UDM, UDR. I believe the PCF is also, there's some policy control, so it's getting policies from the PCF here. And then what we're not seeing going on in this, because we're just looking at the 5G core, is at the same time the G-Node B is setting up the RRC, or the access stratum security algorithms, with the UE as well. So that's just the RRC security mode command and security mode complete from the UE to the G-Node B, and that's to verify the integrity and set up integrity and encryption of RRC messaging from this point on.